guys, and welcome back to my channel. Ever since Einstein created space-time theory in 1905, all physicists around the world were using Minkowski space to represent the relationship between space and time. But what if you could make it simpler? What if you could represent it on a piece of paper? Well, today we are joined by the amazing scientist Terry Bollinger, who we have already had on this channel once, talking about black holes, but today we're going to be talking about physics to visualize the space-time theory in a much simpler way. So make sure to watch the video on black holes and hope you enjoy this video.
I've talked to physicists who've been very surprised to see that this works because they're so used to doing it in a more complicated way. Most physicists consider these transformations to be essentially magical. There's a tendency towards a mystical interpretation of these accelerations, and you can't do it. You can't make these systems work. I sat a good 10 minutes when I first tried that out. There's got to be something wrong with this, but that does not seem to be the case. And it opens up the idea that special relativity has closer ties to other parts of physics.
Hi, I'm Ettan, and on this channel, some of the brightest minds meet. Welcome. Hi guys, I'm here with Mr. Bollinger for another amazing interview, and today he's going to be sharing his amazing insight on space-time. And last time he was able to share his insights on black hole. So welcome here, Mr. Bollinger. And I believe you have a theory which takes space-time and represents it and really explains it in a more simple way in Euclidean functions and graphs. Is that correct?
That is correct. It's essentially taking the same concepts, same predictions with additional predictions, and that's important, and expresses it into the way that we just normally do graphics and do geometry.
So it's taking the Wisconsin and it's making it simpler.
Yes. The original representation of special relativity, the most common one, is to use what's called a mixed signature space, which is a fancy way of saying they stick a minus sign in there for time. And you get it's a very effective theory. That's not the problem. Question is, from an algorithm viewpoint, does that need to be there or can you make it simpler? And that's what this is. This is a way of looking at, say, well, what if we don't do that? What if we actually just use ordinary space? And interesting things happen when you do that. They still give the same results, but they also give some additional results and put some constraints on how we go about doing special relativity.
Amazing. So today you're going to explain what is space-time, what is Euclidean functions, what is all of this, because I'm sure a lot of people watching might not know. And yeah, I guess let's just get started.
Okay, sounds good.
So here, guys, we see the Euclidean square space-time for special relativity. And Mr. Bollinger is going to, explain to us, what is this?
This first picture here shows ordinary graph paper. This is just what you might use in school. You have the idea that there's time zeros down at the bottom, as represented by the little clock on the left. And then you have an end time at the top where the clock has moved further. This might be 1 hour of time. It might be 1 second. The actual scale doesn't matter. It can be very small, very large. So then you have an object, and the object moves through time. And you wind up with the second representation of the object at a new point in time. When they talk about space-time, that's really all they're talking about, is the idea you have space, and then you have this other axis. In this case, we're borrowing up and using that to represent the progress of time. So it's a straightforward concept. We see it in all sorts of graphs and charts, and there's nothing novel about that. Now, the question is, I think what special relativity is all about is what happens when you accelerate an object. Because physics gets a little strange when you get to very high velocities. And we've all heard this idea, the speed of light is the limit. Well, the speed of light in this figure is the upper right-hand corner. So you've got the distance and you've got the time sort of squared off, so they're a nice even path. And you can't go any faster than the speed that takes you to that upper right corner. So you launch a ship, accelerate it, and you wind up there. Now that's a very fast spaceship. That's one where you had an initial launch and everything else is just coasting, it's just moving along. So you're not continuously accelerating. But that one's going at 86.6% of light speed, which is an unbelievably high and hard to reach speed. But you can do it, and you can certainly do it with things like atomic particles and particle physics. They do this all the time. It's much more difficult with large objects, but the math stays the same. What you find out with these ideas for a small object also apply to large objects, like GPS satellites. Now, the next step, here's where we start the Euclidean method. By that I mean we just take graph paper. That's all Euclidean means in this case. It's just take graph paper. You don't have to worry about space. And you drop a line from wherever the spaceship landed and down to the bottom. So, and then the next step is to draw a new line that goes along the same path that you had when the object was at rest. So that's always your reference point. You say, what did the object do when it was just at rest, when it was not moving? Turns out there's a very important piece of information. And we represent it as a special arrow that has a length that doesn't change. No matter what you do to it, it stays the same length, even when you turn it to the side, which is what we do next. We start rotating that line until clunk, it hits that dotted line on the right. Now, this is, again, just simple geometry. You can do it in a graph. It's very easy to do with pencil and paper, but the meaning of it is important. So you take this invariant line, this representation of how time can be transformed, bump it against that, and now you have a little bit of geometry here. And the next step is to draw a rectangle. And there's the rectangle. So what is this rectangle? With that rectangle, this is actually surprising. It also is surprising to physicists. I've talked to physicists who've been very surprised to see that this works because they're so used to doing it in a more complicated way that the idea that you can do it on a piece of paper just doesn't feel right. And what it is that the height of the rectangle is the amount of time that goes by on the spaceship. So the ship elapsed time is half that of the ship that was at rest. And you see that just by looking at the time chart. You've got the same time chart you used when it was at rest, but now you use the leaning line and the rectangle that it draws to figure out what the ship time will be. This is also called the Lorentz factor, and it gives you pretty much the reason why you can't go faster than the speed of light, because time comes to a complete halt if that line gets too far down. The bottom bracket just tells you how far you did in the travel, so you have the distance. So you have, and now what's interesting about that, you know what the distance is, so there's nothing novel about that. You've already marked that out. You now have the time. What is interesting about this is a very literal transformation of space and time. You've heard the idea that space and time are interchangeable in special relativity. That's what this rectangle is. It's saying that if you're completely vertical and the rectangle is just a little line going up, then it's all time. But as that rectangle gets farther and farther to the right and eventually ends up as a flat line, that means that you transformed all of your time available to you in the spaceship into travel. So it becomes a distance, but you do that distance without elapsing anything in time. So at all points, the transformation between space and time, between the vertical time and distance, is just how you draw the rectangle with this one special angle that always stays the same length. So you can just graph it out and there you go. That should be enough on that one. So just getting the idea that you can use simple graphics to convert between space and time covers the main message of it. Now, what's interesting about the diagram I just showed with graph paper is if you want to make calculations precise, of course, you need some mathematical notations. So what we want to do is take that idea and transform it into something that is more precise mathematically. That would then put it into computers and use it in real problems. So this next figure shows the idea of a coordinate plane again, which time is vertical going up, distance is horizontal going sideways. But now it's got some funny notations on it. This is an important thing in math. You don't want to let the notations throw you off from the intuition about what they mean. So for instead of y, I have t times a quantity called I. And I is a fascinating quantity. It's the square root of -1, which baffled mathematicians for centuries, literally. But it turns out it's a very useful way of representing things mathematically. But to use it, you just treat it as saying it's more or less the same as y in this context. So you have x in the bottom, distance. You have y in the going vertically, which is time. And then you have on the left, you have a coordinate point that is somewhere in the original object that you're wanting to accelerate, that you're wanting to move into a new velocity. So that is a coordinate, and you express it, instead of having x and y, you have x and a quantity multiplied by eye, and you do it as a simple addition. But it's still just a coordinate. It's just still 2 points, one horizontal, one vertical. The green dot at the center is very important. That is the front of whatever the object is that you're accelerating. And this is a point that is not called out in most versions of special relativity, and that's unfortunate, because until you recognize the importance of the first point in whatever the object that's accelerated, you can literally wind up with time paradoxes. You can wind up with things that don't make any sense and just make your mind kind of go like, "Oh, what's going on here?" And you don't want that. This is science. You want to be able to say, what's the prediction? What's it going to do? What's going to happen? So you get that green point, which is the front of the system at launch, before it accelerates, comes the coordinate in this new time system. Then we get back to that rotation idea. Remember, I showed that colored line just falls over in one direction. Well, it fell over by an angle. It could be 45 degrees, 30 degrees, 60 degrees. Here it's doing that again. So again, don't lose the intuition. The intuition is that it's the same angle, which we call theta, a little notation, and it has a mathematical representation, which is it's delightfully complicated and simple at the same time. It's what's called an imaginary exponential. And the reason they use this thing, because E is a strange little quantity that you don't run into in most cases in ordinary mathematics or ordinary geometry, but you take this to an imaginary exponential and suddenly becomes a way to rotate things very, very easily. So that happens in math sometimes. You get complexity that leads to simplicity. In this case, a single multiplication by this quantity called e to the I theta produces a rotation of that point. So you see the rotation here from the black dot, it goes over to the white dot, and that's your new set of transformed coordinates. So you get a nicely easy way of doing this. Also, in terms of computation, is very straightforward. This technique is used a lot in quantum mechanics because you have a lot of rotations in quantum mechanics. So you'll see this e to the I theta notation very often if you look at a quantum mechanics book. Now, when this came up, and I was trying to do the representations in a simpler and simpler form, when I got to this point, my reaction was literally, it can't be that simple. it just seemed too simple. So, and yet that's where I could not find an example. It works. It works for whatever point you might have. Now, next, we have the issue of measurement. Talk about measurement. We talk about measurement in quantum mechanics. Turns out measurement is extremely important in special relativity. Why is that? Because when you accelerate a particle, when you accelerate a spaceship, you create its own unique set of length and time measurements that don't match anybody else's. So you go like, well, okay, where did it drift off in some different universe? No, it's still there. It's still right there in your universe. You can see it going by, and you don't want to lose that intuition. You want to realize measuring is something that you can do at all times, including special relativity. And it seems like a straightforward point, but it is remarkable how much it confuses people sometimes. So you can always set up little measurement devices along the path of the spaceship, and they can look at it and see what's there and see what the time is. The blue dot is the measurement of that new coordinate system. When you're measuring it there, it has the whole set of devices that give you, here's the time in the original rest frame, and here's what that point in that spaceship looks like at exactly that time during its journey. This has all sorts of interesting effects because people who've heard of special relativity hear that things are not simultaneous. And that's true. And if you use this technique, you find out that the different parts of the spaceship are no longer simultaneous with themselves. They don't have the same clocks. So the back of the clock will have a different reading from the back clock in the spaceship will have a different reading from the front clock. And you'll see that when you use these at-rest measuring devices, which you can always do. So the danger in special relativity is you can get kind of overly mystical about it and say, until we actually measure things at the end, nothing is set. That could not be farther from the truth. The universe is filled with photons. The photons are constantly colliding. Those are causing images of what's going on in the outside universe. This is all, in a sense, being recorded by the universe itself if you have light there. You want to make sure that you don't make the mistake of thinking that suddenly these things floated off and that you can't watch the changes in time happen. You can always watch it.
Thank you for taking your time. It's really amazing so far. Actually, how long have you been doing this?
Working on this?
Yes. How long?
Special relativity. I've been working on special relativity for I guess, decades. I've always found it intensely fascinating.
I mean, this theory specifically.
This theory, the tilted block representation, which we have not really talked about, but the tilted block representation was something that October 28th was
Of
when I
this year?
came up with this year, right before you guys came to visit, the day before. The tilted block is what leads directly to this, because the tilted block shows us an invariance that applies to all points. So from that, the next simplification was the imaginary complex. So all this came out of that since October 28th. And the imaginary is maybe a couple weeks old. So it's very new, but also very simple. So that's the other thing about it is you can give it to pretty much anybody and they look at it and say, well, here's what it does. And here's what special relativity usually says. So the main difference is it makes more precise predictions and puts constraints on the idea of acceleration. Now, this final slide talks about this whole idea of tilting that extended line from an important viewpoint of how do you accelerate a large object. Something like a train is the example that Einstein used, but also a very real example is actual satellites that we use in space now. GPS satellites are an example of that. And this example is good because one of the distinctions of this approach on special relativity using a fully Euclidean approach is that you have to take careful account of the steps of acceleration, that you can't just assume that nothing changes, that it just sort of goes into a new definition of space and time. But what you actually have to do are very specific steps that involve real mechanical changes to the system. So this contradicts the idea that these different frames are completely interchangeable, because if you change the physical configuration of the system, as Einstein himself said in a footnote, then that creates a need for more complicated math. So anytime you try to move a set of satellites into a new definition of space and time, an accelerated definition of space and time, first thing you have to do is select which objects you have. The one on the right becomes the front. Again, that front is very important. You squeeze the objects, and that means you have to move those satellites. And if those satellites occupy, say, most of the solar system, you could have satellites between Saturn and different planets, and you want to have them all in the same inertial frame. That takes time and can take a lot of time. So it's not a trivial part. Squeezing is the same thing that's called Lorentz contraction. And people think of it as kind of a thing that just magically happens. It's not. It's a real, completely physical contraction that must take place during the acceleration. And that is a different perspective, what you see in many cases. The third step is that you have to change the clocks. And when I say change the clocks, you have to reset them in the same sense you do when you have daylight savings time. The clocks at the back have to actually be moved forward. You can actually have a scenario where a person has to go to the back of the satellite system and manually cranks that clock and say, oh, I've got to set this thing up to a new time. There's nothing abstract about this. This is a physical transformation that must be done in order to make the new system work. So when you do, yeah.
I never think, when I first saw this, I was like, the actual physical turning of it. I don't know why, but it's just, when I think of physics, I never actually thought of really getting hands-on. I always think about abstract math, and I never thought, am I really thinking straight that we actually have to turn it?
That is a great insight, Ehsan, because this is one of the things that slows down comprehension of how to calculate these processes. If you have only the mathematical abstraction, and if the abstraction is a little too simple, then steps like this just get kind of squished together and you don't realize that some action has to be taken. So the idea that, for instance, Lorentz contraction requires actual fuel-propelled movement of satellites into new positions is not a common image that people have in their head. And yet, if you want to move that set of satellites into a new system, into a new space-time system, coordinate system, you have to do it. And that means it's going to take you time. If these satellites are far apart, it's going to take you a lot of time. It's going to take you fuel. You have to actually, turn some jets on and move the satellite. So Lorentz contraction is far more real than people often perceive it to be. They think it's some kind of an abstract way of looking at the satellite system, but it's not. You have to actually move things. And that's one of the points in this. Same thing for the clocks. People often get the feeling that there's time paradoxes in special relativity, that things can can be in the past or in the future. And this is where you get the idea of a block universe, by the way, is people get very kind of loose with these time definitions. But if you realize that you have to physically go back there and set the clock into the future and say, oh, well, I just lost an hour, sort of, but not really, because it didn't go by. You didn't see any time go by. You didn't spend any time doing it. You just changed the clock. The idea that you have to do it that way makes you realize, no, there's no time paradox there. I just went into daylight savings time. So daylight savings time is not a paradox. Neither is this. There's no dipping into the past or dipping into some unknown view of the universe. Then the final step, which is, again, more explicit in satellites than it is if you try to do it with trains, because trains are all connected, but satellites aren't. So you have to say, oh, what do I have to do to each satellite to get this working? The final step, and you can actually change the order of these steps, but this is the simplest way to think of it, is then you accelerate the satellites all separately. And you go like, why is this so complicated? Well, the reason it's complicated is all of these are parts of how you set the state, the internal state of the satellite system, so that it can accommodate the new definition of space and time. And you have to do these individual steps.
Sure. Just one question. So, is daylight saving time when you just make the time go back by 1 hour or 2?
Daylight savings time, when you either set it forward or set it back, and it's an idea of how you coordinate time with other locations. And the same concept applies for large objects under special relativity, that you have to essentially create time zones in preparation for them to all then view themselves as being simultaneous. This is the strange thing about this, is once all these clocks are set, and then you do that final step 4 of acceleration, those same people will look at their clocks and say, oh, now we're perfectly in sync. And the guy at the back says, what do you mean we're perfectly in sync? All I did was change the clock manually. How come you're suddenly simultaneous with me? It's a very kind of a mind-bending concept that he manually changes the clock, and then he finds out, oh, now I'm simultaneous after I do the acceleration. And all of this has to do with the way the delays and speed of light on how it works out. But they can't tell any difference after they've done that.
So by turning the clock, not only did it, of course, well, it's like in a different country, of course, it would adapt and it would change the time, but it would also, you're saying, like, make people feel like they're synced with the time?
Yeah. And when we do ordinary daylight savings time, people don't feel like they're synced. Like when we prepared for this, we're in different time zones. The marvelous thing about special relativity, about the Einstein contractions and transformations, is that once you do these, you don't feel you're in the same different time zones. You could do this with literal time zones, or it would be rather disruptive to the Earth to have pieces of it moving that fast. But you could actually have pieces of the Earth move fast enough in one direction that suddenly your time zone would become the same as my time zone, and we would suddenly see it as being the same time. So this is it's kind of a wild idea that you can make the time zone difference into simultaneity. But of course, that's the whole idea, is that simultaneity is relative to the observer. There's another simple, important point. Remember, I talked about the Euclidean space, the idea that this is Euclidean special relativity. You never lose the original coordinate system. When you take these satellites and you move them and you change them and you alter the clocks and put them closer together, all of this is still being done in the original coordinate system. So if you have complicated sets of different frames moving at different speeds, you can always fall back to that original coordinate system and say, how do I make this just simple graph paper again? And that's very handy. That's very handy, because sometimes these systems can get very complicated in resolution. One of the areas where I'm most looking forward to further elaborating on this is the complicated cases where you have things bumping into each other at high velocities. This winds up giving more specific predictions about that, and I think interesting ones. Most people in special relativity, most physicists, consider these transformations to be essentially magical. That may be an overly blunt way of putting it, but there's a tendency towards a mystical interpretation of these accelerations, and you can't do it. You can't make these systems work. You can't keep your GPS from driving people off a cliff unless you take these effects into account. You have
That's GPS. I'm sorry, I thought it stood for something else. But okay.
Yes, the global positioning satellites, the GPS systems. Yeah, when I was given this as an example, that's intentional, because they do take these effects into account one way or another in the GPS satellites. What this is saying is if you want to have it as a single inertial frame for the satellites, here's the steps that you have to do that. There's potential for some mathematical simplifications and how they coordinate GPS systems. Those are very complicated. You have to take gravity into account. It's not just this flat Euclidean space in the case. You have gravity. But nonetheless, these issues apply to actual satellite systems that exist. And we have clocks that are so precise that all of this is measurable. This is not abstract. You have to have actual accounting for the clocks.
Sure. Okay. So to finish off our amazing interview, Mr. Bollinger, is there any way that you'd like to wrap this up or even conclude this amazing interview?
Thank you for the interview. I thoroughly enjoyed your questions. I think the most impactful part of this approach is that it's not something that you can just partially do. You have to take pretty much the entirety of special relativity and convert it into what's called a state machine mechanism, which we haven't talked about here, but it's very closely tied to those different measuring systems. The measuring systems are the states, and those define how you have space and time. So what I'm seeing for this in the future is just a very different computational basis for assessing some of these problems of special relativity. And one's actually simpler in many ways. It'll be more multiplications and give more specific answers about, what are the clock settings? What are the times? How much time does it take to accelerate an object? What are some of the different ways you could accelerate an object? All of these are questions that open up. The other set of questions it opens up is what happens when you take this down to the atomic and particle level? And I am definitely looking forward to exploring that part because these formalisms are the same ones. So that doesn't seem like a coincidence. If special relativity suddenly becomes phase transformations, as they call it in particle physics, then probably the particle physics have some kind of closer connection to these representations than we recognize. I think some intriguing possibilities with that. The other direction is general relativity. Haven't even looked at that yet. Well, that's not entirely true, but I think if you change special relativity, you have to change general relativity in some fashion. At the very least, you attach general relativity much, much more tightly to matter and energy. No matter and energy, no curvature of space, no space at all. That's a very different perspective from what you usually do. You wind up with the same representations, the same curvatures, but the implementation of the curvatures is very different.
Sure. Well, thank you so much, Mr. Bollinger, for this amazing interview.
Thank you.
And it's nice seeing you once again.
Good to see you. It's good to see you again.
Thank you.